Section 4.1 is entitled Congruent Figures. So we're going to talk about what makes figures congruent and how we use congruency when we're talking about geometry. So we have to remember our definition of congruency, which means same size, same shape. So if I have two figures, like the two right here, they are congruent as long as they are the same size and the same shape. So size would be kind of like their area, and shape would be what their angles and segments measure. And as you can see, these two fit directly over top of each other, and they're the same exact size and shape. So when we talk about two congruent triangles, obviously they will be the same size and shape. So that means the corresponding pieces are congruent. So when I look at two triangles, if I have two of them like these two, and I label this the angles and segments with letters here, so we have each vertex as a different letter. So I have triangle FUN and triangle GEO. I would say that since the corresponding pieces have to be congruent, then angle F and G would be congruent, O and N and U and E. All the angles have a congruent partner. And the sides all have congruent pieces. So when I'm given that two triangles are congruent, the corresponding pieces must be congruent. So if I'm told that this triangle FUN is congruent to triangle GEO, then I can therefore conclude angle F is congruent to angle G, angle U is congruent to angle E, angle N is congruent to angle O, GO is congruent to FN, the segments, and so on. Okay. Here's a couple conclusions we can make. So our reason for saying that those pieces are congruent would be CPCTC. Now a lot of times the book just does CPCT, which is fine also, saying that they're the corresponding parts of congruent triangles. CPCTC. I just say that they're congruent at the end. So that's our reason when we conclude that two of the angles are congruent or two of the sides are congruent. So if you're given that ABC, triangle ABC is congruent to triangle XYZ, we can then conclude that angle B is congruent to angle Y. And the reason is CPCTC. And there's a lot of conclusions we can make. So I just put a couple here. So when we name a congruence, it's important that the corresponding pieces line up. So when I say I have a quadrilateral here and a quadrilateral here, I would say that since this angle lined up with this angle here, even though I twisted this, when I name the congruence, these two have to be in the same spot in the congruency statement. So if I just give them different letters here, now I do realize I have two angle A's. We could pretend that these were attached here. I would say angle A here is congruent to angle L here. So we can say quadrilateral LFHA is congruent to quadrilateral ARBE, and FLAH and quadrilateral RAEB, and quadrilateral half and quadrilateral bear. Some examples. Just a moment here. Sorry about that glitch there. Had a little bit of an interruption. Here are some examples. Always, sometimes, never. An acute triangle is always, sometimes, never congruent to an obtuse angle. And of course, that's never true because you wouldn't have an angle, a right angle in the obtuse triangle to be congruent to the right angle in the right triangle. 2, a polygon is always, sometimes, never congruent to itself. Of course, always. The right triangle is always, sometimes, never congruent to another right triangle. No, sometimes. If triangle ABC is congruent to triangle XYZ, is angle A always, sometimes, never congruent to Y? Well, here's A, which we know is congruent to X. But do we know it's congruent to Y? Well, we don't know that, but it could be by coincidence, so we're going to put sometimes. Now, if we have the same statement and we say B is congruent to Y, look at that, B and Y are corresponding, so they're always congruent. And with ABC congruent to XYZ, if AB is always, sometimes, never congruent to YZ, here's AB, here's YZ. Notice they're not corresponding parts, so they could sometimes be congruent. Suppose triangle TIM is congruent to triangle BER. the following. What's IM congruent to? We look up at the statement and we say, oh, IM is congruent to ER because they're in the same spot. They're corresponding. And the angle congruent to angle R, well, angle R is the third one here, so it's going to be angle M here. And if I were to change the order and say triangle MTI, MTI is congruent to, it would be RBE. And the last one, if triangle ABC is congruent to triangle XYZ, and B is 80 and C is 50, name 4 congruent angles. Now, since I want 4 congruent angles, I'm just going to draw a triangle here, and a triangle here. Now, I'm not drawing this very well to scale because it's very slow here. But if we have angle B and C are 80 and 50, I'll just make this 80, and I'll make this little one 50. This isn't going to be drawn to scale at all. There's my 50. Do you see that we have 2 angles of the triangle and we can actually find this third angle, which happens to also come out to be 50. So since this was ABC, angle A is 50, angle C is 50, and A and C are congruent to X and Z. So X and Z are both 50. So our solution for this one are angles AC, X, and Z, all 50 degrees. All right, we'll do one more example just for fun. This one's kind of a fun one. We say the true triangles shown are congruent, and I said triangle NI sub 1, just to differentiate between these two ends, is congruent to triangle what? And that's triangle JAS with corresponding pieces, which of course spells inches. That was our fun moment for the day. That's the end.